magnetic volume. So let me tell you, if a sample, the first at high temperature is non-magnetic, at low temperature it becomes ferromagnetic. The magnetic volume in the ferromagnetic state should be 100%, which is 1.0. So we measure several nickel-rhodium alloys, and it turns out for the X smaller than 0.375, magnetic volume always reaches 100% at 2 Kelvin. But once I measure the 0.375 sample, so this is temperature, this is magnetic volume, the magnetic volume for 0.375 is always 0. That means my transition, the transition remains second order up to the critical concentration. For comparison, this is another ferromagnet, magneticity side, and the tuning parameter is pressure. So again, the magnetic volume versus temperature, when the pressure is kicked in, the temperature shrinks. The temperature is suppressed, the ferromagnetic temperature. But at the same time, the magnetic volume also shrinks. That means the transition becomes first order. So now we are confident we have a quantum critical point in this region. Then we start to measure thermodynamic properties. I measure specific heat, and as you can see, again, this is C over T versus log T. In the vicinity of the critical concentrations, all the data shows logarithmic divergence. And my colleague measures thermal expansion, which measures how the length changes as a function of temperature. This is also a measure of quantum fluctuations. And again, Fermi-liquid behavior predicts alpha over T should be a constant for a metal. But instead, for our sample, alpha over T varies with log T. So together with 2, we can further calculate so-called Green-Einstein ratio, and that's gamma, defined by the ratio between this and that. And this term has to diverge as well. And mathematically, that means the alpha over T should diverge faster than C over T. And we prove that. So for this paper, we claim that we found a ferromagnetic quantum critical point for nickel-rhodium alloy. This is the summary. I show you that I can use chemical disorder as a control parameter to tune the FM QCP. And that's in line with the BKT theory. And I've shown you 2 experimental results. As I said, I already told you that I don't have superconductivity in both of these materials, and hopefully one day I could have that. Thank you for your attention.